Okay, this tutorial is just going to go over quickly how to use Tracker to analyze that the rubber motor. So the first thing we're going to do is just go online and find Tracker. And we'll do that somewhere else. We'll do that in here. Download Tracker for physics. Okay, there we go. And the version that you want to download is the jar file. So find the latest jar file and download that. And we'll keep it. And once it's downloaded, we will open it. And we should get a window that looks like this. And the next thing we want to do is just drag our video file into there. And so our video file is, I saved mine in here. I put it up in the forum on our Empower page as well. And we need to film this at 1000 frames per second, otherwise it gets too blurry. You'll see that it already gets quite blurry at 1000 frames per second. So it looks like this. Then we want to identify where we want to start the video. So we'll find out where it starts spinning, which is about there. And I'll move that up to there. Just so we don't have to watch a whole lot of unnecessary frames. Then we'll identify where it stops spinning. Okay, that's where it stops spinning. And it's actually spinning the opposite way at the end because it bounced back a bit. But we'll stop it from when it's stationary, then we can talk a little bit about what happens there. Then we want to change the frame rate, and we do that by clicking on this little film clip icon. The frame rate here was 1000 frames per second. Okay, and we will increase the step size, otherwise we'll get occupational overuse syndrome. So we'll make it 20 frames. You might want to make it less if you want a smoother curve, but I'm going to do this just for expedience. We'll go back to the start there, and then we want to add an axis that's centered. And I pressed the axis and it didn't appear. That's because I think it appeared somewhere in the wrong place. So I'll just zoom out, and there it is. Move that up to the video that I want to look at. I zoomed out using the mouse wheel, by the way. You can also zoom out using this zoom button, and you can just click that to, or yeah, you can zoom with that. So let me just zoom back in. Okay, now we want to create something to track. So we create a point mass. And because what we're going to be mapping is angle, we'll change this to angular velocity. And then what we do is we hold down, we'll click on this mass A, oops, and then we hold down Shift, and when you do, you should get this little crosshair icon. And then we just click on the frame that we want to track. You can see that it's moving now. And it moves quite far with each one, because I'm only tracking every 20th frame. You could do more frames. In fact, I think I'm doing too few frames. It's not picking up. It's not picking up enough. So I'm going to go back. I'm going to delete this track. And I'm going to change this to other, to 10 frames. Or maybe even to 5 frames. I just won't track the whole thing because it'll take too long. Then go back to our starting frame, and then we'll create a new point mass. And yep, and then I'll hold down Shift. You can see that now I'm tracking more frames. It's not rotating nearly as far each time, and it's able to identify that it's not moving backwards, because before it was jumping back and forth. Okay, and just carry on like this. I'm just going to change this to angular displacement. No, I won't. I'm going to change this to angular velocity. going like this, you can see that its angular velocity, if you look at the graph on the right here, it started at 0, and because it's spinning clockwise, clockwise is considered a negative angular velocity on this reference frame. And so it is actually increasing, which is encouraging. So with every frame, every 5 frames, you see that it's getting quite blurred now because it's moving quite quickly. And let's keep it going. It is flattening out. It's reaching its maximum speed here. And I'll keep going until... oh, actually I'll just keep going until it stops the first time before it's bounced back. Okay, this is a reasonably tedious process. It takes quite a while. And now it is starting to slow down again. Okay, you can see I've already tracked 104 points. And it's now getting nice and slow again. The rubber band is almost completely untwisted. And now it's stopped. If I continue further, it'll start spinning the other way, which might be an interesting thing to analyze eventually. You can see what we got here is this nice kind of well, it's quite a nice symmetrical graph where the angular velocity increases to some maximum value, which looks like it's about negative 2.3 radians per second or something like that, and then it decreases back up again to 0. In fact, I should just plot one more, and then it reaches 0. And what we can do now that we have this plot is we can add a new parameter here. If we right click there, we can define a new one, and what we want to do is add one, and we'll call that rotational kinetic energy over, no, we can't use over I. And I'll explain what that means later. And the expression for this is half times, and we want omega, which is there, which is the angular velocity, and we're going to say squared. The actual equation for rotational kinetic energy is half times I times omega squared, but I is constant because we haven't changed the rotational inertia of the system. And if I is constant, that means that the rotational kinetic energy is proportional to this. It's not equal to this, but it's proportional to that. So we'll leave it at that. And then we'll close this. And now we can plot that against time, which looks like a, well, it looks almost like a bell-shaped curve, but we'll see what kind of curve fits it best later on. And now the other thing we can do here is, is we can change the data that we have here. And we can have, we don't need x and y, but we do want t. Well, we want omega, and we want this new thing that we defined. So now we have all this data here, which we can take and put into a more convenient graphing program. So I'll just cut that into Excel, where I can manipulate it a little bit. Oops, it needs to cut after I've opened Excel. And I'll paste that into Excel. And here's all that data. Now, what I really want is not just the rotational kinetic energy at any one given time. I want the total rotational kinetic energy given out throughout the whole motion for each time. And so that's going to be equal to, so this is total RKE. And at the first time, that's equal to that. At the next time, that's going to be equal to the previous one plus the next one. And because this one here is so small, it hasn't really changed at all. But now what I'm going to do is I'm just going to check that that's working. It's gradually increasing. Yep. And then I'm going to go all the way down to the bottom. And what this column then has is the kind of cumulative sum of all of the rotational kinetic energy up to that point. This column is the instantaneous kinetic energy at that moment. This column here is all of the kinetic energy produced in total up to that moment. And I'll explain why we're doing that in just a moment. Then I'll take all of this data like that, and I'm going to put it into LoggerPro. And now I've pasted that into LoggerPro and I've got all of these things. So now I want to just rename these so that I don't get them confused. I'll go to column options, dataset X. This is time, and that's in seconds. This one is the angular velocity. Short name is Greek lowercase, whoops, not alpha. It is omega, not alpha omega, just omega. And that's in radians per second to the -1. This one is this is the rotational kinetic energy over I. We call that RKE over I. And the units for that was going to be joules, but because we've divided by I, it's going to change the units. So it's going to be joules per kilogram. This physics, this stuff I can help to explain. When we're going over it. It's going to be the unit for rotational inertia is kilograms per kilogram meter squared, and we're dividing by both of those, so it becomes joules per kilogram per meter squared. Okay. This is the total kinetic energy produced per I. And the short name is RKE total over I. And the units are the same as the last one. Joules kgm. Like that. And now what we want to have a look at, well, if we plot angular velocity against time, it looks like that. If we plot rotational kinetic energy against time, it looks like that. If we plot total rotational kinetic energy against time, it looks like that. So initially it's spinning quite slowly, and then it increases in velocity. And here it's spinning at its maximum velocity, so the rotational kinetic energy produced is increasing rapidly. And then it stops, and when it stops, it's produced all of its rotational kinetic energy. That's not quite what we want either. So we want to put in a new one. So we'll create a new calculated column, and this is going to be the power. And the power is just going to be the time derivative of the total kinetic energy produced. It's the total kinetic energy produced per second. Well, basically, it's the gradient of this graph at all points. So what we're going to the way that we do that is we use a function. We go to calculus. We create derivative, and then we add a variable. And the thing that we want to create a derivative of is the total kinetic energy produced, like that. And then we click. Well, we should call this also power per unit rotational inertia. P over I. And the units is watts per kgm squared. Okay, now we can plot the power output. And this is exactly what the question was asking for. Investigate how the power output varies with time. So this tells us. Now this program stupidly joins the dots between all the data points. We can undo that like this. We go to graph options and we unclick connect points. Oh, I got to graph options, by the way, by just right clicking. And we get the scatter of the points instead. And now we can analyze and we can fit a curve to this. And I don't really know what kind of curve this is. Maybe we can try a Gaussian, which is a bell-shaped curve. Does that work? No, it doesn't like that. Oh, it looks like a nice sine curve, but I doubt that it's a sine curve. Anyway, so, and you can also here define a function. If you suspect that it's a particular kind of function, then you can define it in here. We won't bother with that too much. What we'll do is, in fact, I'll just join the dots again so we can, in fact, I'll put point protectors on them. So there's our graph of how it evolves over time. The next task, once you've gathered all the data for all the different variables, is to explain why on earth this should be the pattern. Why should it release energy slowly initially and then very rapidly for a short amount of time and then die away again? Okay, so I hope that clarifies how to do this, how to carry out this process.